What we've got right now is a very nice problem which asks us to think about a very simple structure loaded in a fairly simple way and think about how the moment around point A is affected by the orientation angle theta of this 40-pound force which is applied out at the end of the L-shaped structure. In particular, what we want to do is find theta such that we can maximize that moment and also find theta such that we can minimize that moment. So there is a really good connection here between the physical interpretation of what a moment actually is in terms of a force and a moment arm, and the mathematical interpretation of this, which is extremizing this moment, making it a maximum or a minimum. And so throughout this problem, we're going to go ahead and look at both of those points of view. Let's go ahead and write an approach for this. So step one is going to be to consider the physical interpretation. And in particular, we're going to think about some mathematical tools which will help us connect the math to the physics. Second thing we're going to do is do a cross-product type calculation. And we're going to do that in a fairly generic way. And what we're going to do with that cross-product calculation is we're going to do this maximization and minimization kind of an operation. And if you think about how that's going to go, you can imagine that it's going to be a differentiation. And then we're going to set equal to 0. And what we're going to do there is we're going to find theta, which maximizes or minimizes the moment. From there, we're going to go ahead and solve for what those moments are for the two cases, the maximum and the minimum. And then as step 5, I'm going to insert a little note here to kind of check, because I want to make sure that the math that I work out in step 4 is in line with the sort of physical interpretation and the intuition that we provide here in step 1. Okay, so what I'd like to do is actually just start step 1 right here on this page, and hopefully you'll be able to sort of follow along and see what's going on here. So step 1 is a physical interpretation. And there are two cases here. One is when A is going to be is when the moment is going to be a maximum. And that's going to be, as you might imagine, when the force is oriented at a line perpendicular to the vector which connects point A to the point where the force acts on the structure. So if I imagine a line here that looks something like this, you can imagine that the moment is going to be maximized when the force is oriented perpendicular to that. Okay, so we're talking about a triangle here, something like this. So here's point A. Here is my moment arm, and in the parlance of a moment calculation by cross product, we're going to call that R. And then what I'd be looking for is an F, which is perpendicular to that. Now, based on the geometry that we have here, where we've got this distance here of 2 and this distance here of 8, what we can do is we can figure out that this angle is actually about 14 degrees. Okay, so that means that this angle up here ought to be 76 degrees based on our physical kind of interpretation of the problem. Okay, so what we're expecting is that in step 4 we should be able to solve for an angle of about 76 degrees to get this to happen. If we want to minimize the moment, we know that one way to do that is for the force to go directly through point A to make the moment arm effectively 0. And the way we might do that, here's point A, is to choose an angle such that the force is directed exactly back through point A. And so based on the geometry that we just did, you can figure out that this angle then would have to be 166 degrees. So it's basically 76 plus another 90 to get it to point back towards A. So we anticipate that in step 4, when we solve for this angle using a moment type calculation, we should get 166 degrees as the magic number which will minimize the moment. And of course the moment that results in this part B is going to be 0 because the moment arm itself is going to be 0. So we've got some intuition here about how this is going to go just by doing some trigonometry and applying some physical interpretation to what we know about moments. Let's go ahead and actually do the math and make sure that it works out the way we think it's going to. So step 2, we're going to compute our moment using an R cross F kind of calculation. Okay, so let's go ahead and write what R is. So from the previous page, you saw that R was going to be equal to 8 in the I direction plus 2 in the J direction. That's going to have units of feet. And I guess I should come back here and say I'm sort of implicitly using a coordinate system that is X and Y, just like that. Now the moment, the angle theta is measured down this way, and so when we go ahead and write our force vector, you'll see how that plays a role. So we're going to write a force vector, which is F is equal to 40, which is the magnitude, and then it's going to be cosine theta in the I direction minus sine theta in the J direction. Let me point out a couple of things here. This sign, S-I-G-N sign, is due to theta being defined positive that way. Okay, so it's the convention that we used when we wrote the figure. The other thing I want to point out is that this entire thing in the parentheses here, this is actually a unit vector, and it's a unit vector in the direction of the force F. So then what we can do is we can calculate a moment. Moment around point A is going to be equal to R crossed with F. This is going to be equal to 8I plus 2J crossed with 40 times cosine of theta in the I minus sine theta in the J. And so if we go ahead and carry out the math, we end up with minus 40 times 8 sine theta plus 2 cosine of theta in the K direction. And this thing is going to have units of pound-feet. Okay, so we just did the cross product there the way we typically do. So I crossed with I is 0, I crossed with J is just going to be K, and then J crossed with I is going to be minus K. So we can work out the math and get that expression. So now we know what the moment is going to be as a function of this angle theta. In step 3, we're going to differentiate and set equal to 0. And the reason we're going to do that is because that's how we maximize or minimize a function. So we're going to do an operation that looks like this. Differentiate that expression for the moment with respect to theta. And if we do that, we get minus 40. And then we get 8 cosine of theta minus 2 sine of theta. We're going to set that equal to 0. And what we're going to do is solve for theta, which gives us that extreme value. If we divide through by the minus 40, we get 8 cosine of theta equals to 2 sine of theta. And that means we get tangent of theta equals to 4. And so if we solve that, the arctangent, we get theta equal to 76 degrees. Now that should look familiar. That's what we solved for on the first slide of this solution, and that gives us a lot of confidence that we're moving in the right direction here. So let's go ahead and think about how we're going to continue with the solution here. Let's draw a picture first and think about the relationship between the maximum and the minimum of this angle theta. So if we plot the magnitude of the moment on one axis, we plot theta on the other axis, what we're going to find is that the difference between the maximum and the minimum is going to be separated by some angle. Okay, so here's max value, here's the min value, and that minimum value is down there at 0. The question is, how far do we have to go in terms of this angle theta before we get there? And what we discovered on the front was that this was going to be, on the front slide, was that this was going to be 90 degrees. We know the maximum and the minimum are going to be in the case where the maximum is that the the force vector is perpendicular to the position vector r, and the minimum is going to be when it is in line with the position vector r. And we found out on the first slide through trigonometry that we expect that to be 90 degrees. And so that means that the second angle, the minimum angle, is going to be 76 plus 90, or 166 degrees, as we predicted. Let's go ahead and do the math here and sort of figure out what those max and min values are. So MA, the moment around A at theta equals 76 degrees. That's going to be equal to minus 40 times 8 sine of 76 plus 2 cosine of 76. This is just going to equal to minus 329.8. In the k direction, it's got units of pound feet. There's our maximum. If we look at the min, MA at theta equals to 166 degrees, we get minus 40 times 8 sine of 166 plus 2 times the cosine of 166. And we have to be careful to carry all the signs, SIGN signs, through this calculation. On the one hand, we get this term to have a value of positive 1.94. We get this term, since we carry through the signs, negative 1.94. And so this really does just equal to 0. So the minimum then is 0 as we expected, and it occurs when the force passes directly through point A, when it makes the moment arm equal to 0. Okay, so our summary looks like this. MA max is equal to minus 329.8 in the k direction. It's got units of pound feet, and that's at theta equals 76 degrees. MA minimum equals to 0 in the k direction, pound feet, and that's at theta is 166 degrees. And then if we think about step 5, which is to check, we would say yes, this agrees with our physical interpretation. In step number 1. Let's go back and review what we did. The problem statement here asks us to maximize and minimize the moment around point A, and what that really means is to find the angle theta at which this force acts in order to make that happen. And so we started off with a physical interpretation of what we're talking about here. So we applied some intuition and did some simple trigonometry to sort of figure out what we thought was going to happen. Next we went through and did the moment calculation as a function of theta, and did a cross product r cross f kind of formulation. We differentiated that moment with respect to theta and set it equal to 0 to find the angle theta, which gave us an extreme value. And then we again applied some physical intuition about the situation to know the relationship between the angle we solved for in step 3 and the other angle we were looking for, the minimum angle. We went through and did the substitution and calculated that the maximum was 329.8 in the k direction. That was a negative value. And the minimum was 0 for the moment. And those coincided to the angle theta equals 76 and 166 respectively. We finally concluded that that did indeed agree with what we did in step 1, and our physical intuition was a useful way for us to interpret the mathematics that we did in this problem.